Imagine this. What if we could design the perfect material inside a computer before ever, stepping foot into a lab? Well, today we're diving into exactly that, how machine learning is making it possible to predict the physical world, telling us how material will behave before it even exists. Let's get right into it. So that leads us to the big question, right? How do we escape the lab? For decades, discovering new materials has meant these endless, super expensive cycles of trial and error. But what if we could just bypass all that? What if data could tell us exactly how a material is going to behave before we even go through the trouble of making it? Okay, so to figure this out, we've got a roadmap. First, we're going to define the core challenge. Then, we'll see how we can use physics itself as a blueprint. After that, we'll have to move beyond simple linear models, walk through the actual engineering workflow, and finally, see how the whole shebang fits together into one powerful architecture. All right, first things first, before we can even think about building a model, we have to do something fundamental. We have to translate this real-world physical problem into a language that machine learning can actually understand. And that is the core challenge. So here's how we frame it. In the world of machine learning, this is called a regression problem. We're essentially trying to get the computer to learn a function, the classic y equals f of x. Our inputs, the x values, are the material's features. Think of it like its recipe, its chemical composition, how it was processed. And our outputs, the y values, are the properties we care about, things like its strength or its hardness. The whole goal is to get the machine to uncover that hidden mathematical link between the two. Now, here's where things get really cool. We don't have to start from a complete blank slate. Not at all. We can actually stand on the shoulders of giants and use our decades, even centuries, of existing knowledge in physics as a blueprint for our models. And to do that, we have to give our model a goal, a target to aim for. In machine learning, we call this an objective function. You can pretty much think of it as a scorecard. The model's entire job during training is to get the best score possible, and it does that by making its prediction errors as small as possible. A classic example of an objective function is mean squared error, or MSE. It's a pretty clever way to measure error. It looks at the distance between where the real data point is and where the model predicted it would be. That little gap is called the residual. Then, and this is the key part, it squares that value. By squaring it, you massively penalize the predictions that are way, way off, which forces the model to rein in its biggest mistakes and get more accurate overall. Okay, theory's great, but let's make this real. Let's look at a classic from Material Science 101. This is the Hall-Petch equation. It's a physical law that's been around forever, and it tells us how the strength of a metal is related to the size of the little crystal grains inside it. The general rule is, smaller grains mean a stronger material. And this, right here, is the big aha moment. If you look closely, the Hall-Petch equation maps perfectly onto a simple linear regression model. The yield strengths, that's our target y. The friction stress, that's basically the model's intercept. And the grain size term, that's our input feature, x. This reveals something pretty profound. A lot of these physical laws we've relied on for decades are, in essence, pre-built machine learning models, just waiting for us to see them that way. But, it's never that easy, is it? The real world is often messy, and physical relationships aren't always these nice, neat, straight lines. So what happens when we're dealing with materials that are way more complex? Well, this is exactly where those simple, linear models just fall apart. Take a look. On the left, a straight line is trying its best to connect a material's porosity to its thermal conductivity. And it's a total miss, right? It just can't see that complex S-curve hiding the data. But look at the right. A more flexible, non-linear model can actually bend and adapt, and it captures that relationship perfectly. This is absolutely essential for dealing with the complexity of real-world materials. So to trace these tricky Kirby relationships, we need to bring out the heavy hitters. This is where algorithms like support vector regression and random forests come into play. SVR is great at finding the best possible boundary, even in really complex spaces. And random forests are amazing because they combine the predictions of lots of simple little models to make one supermodel. They're built to find patterns that a straight ruler would completely miss. All right, so we get the theory, we know what models to use, but how do we actually build one of these things? Well, it's not just about picking a cool algorithm. It really requires a disciplined, step-by-step engineering workflow. And this is that workflow. It's a 7-step pipeline that guides us all the way from gathering raw data to actually interpreting our final results. You start with collecting data, then you define your features, split the data, select and train a model, evaluate how it did, and finally, the most important part, You figure out what it all means. Following this sequence is absolutely key. Now, every single step here matters, but I want to zoom in on two that can really make or break your entire project: how you split up your data and how you measure your model's performance. This is data partitioning, and frankly, it's a brilliant idea. You take all your data and you slice it. The model gets to learn from the training set, maybe 80% of the data, but it is never allowed to see the test set. That part is kept locked away for a final, totally blind evaluation. This simple trick prevents a huge problem called overfitting, which is where the model just memorizes the training data instead of learning the real physics underneath. So how do we grade the model on that unseen test data? We use these key metrics. We've already talked about MSE. Our MSE is just its square root, which is super handy because it puts the error back into real-world units, like megapascals of strength. MAE, or mean absolute error, is awesome because it isn't as thrown off by a few wild outliers. And finally, there's R squared. This one basically tells you what proportion of the story your model is successfully explaining. For R squared, the closer you get to 1, the better. All right, time to put it all together. We've looked at all the individual pieces. Now let's see the full architecture that takes us from the laws of physics all the way to a powerful, predictive computer model. This right here, this is the whole journey in one picture. We start with Pillar 1, physical reality. That's where we observe that a material's features drive its properties. Then we move to Pillar 2, mathematical formulation, where we translate those physical laws into objective functions that the model can solve. And we finish with Pillar 3, engineering execution, where we use our 7-step pipeline to build a robust model that, hopefully, gets a nice high R-squared score. So if there's one thing to take away from all this, it's this. What we're doing here is so much more than just crunching numbers. It is the digital optimization of physical laws. We're essentially creating a digital twin of our material's behavior, which lets us explore and innovate in ways that were just impossible before. Ultimately, this whole approach transforms materials discovery from a game of slow physical trial and error into one of elegant, fast digital design. It's a brand new frontier, which really just leaves one last inspiring question for all of us. What physical law will you digitize next?